Bon dia. Avui la presentació va a càrrec de Stefano Tavani, que parlarà sobre models virtuals i l'aplicabilitat en geologia o geosciències. L'Stefano va estudiar la carrera de geologia i va fer un doctorat a Roma i després un postdoc de 5 anys aquí a la Universitat de Barcelona. Després d'això va marxar com a postdoc i com a lector a la Universitat de Nàpols, uns 10 anys, i recentment doncs va ser titular. I recentment ara està a Firenze com a professor permanent titular. Llavors, Stefano, la presentació és per tu i endavant.
Gracias, Eloy. Voy a dar la presentación en inglés porque... just one slide to show you the organization of the presentation. I will talk for about 40 minutes. And essentially, there are 3 blocks. In the first block, which is quite short, I will provide you some basic notion of virtual outcrop models. Then a little bit of math about the digitization of geological surface, including faults and fracture embedding. And last but not least, because we like story, I will tell you a story about the integration of virtual outcrop models and real geological mapping in Southern Italy. So, virtual outcrop models, also called a digital outcrop model, is just the surface-based digital representation of an outcrop that can be not only seen but also navigated and analyzed. In its raw format, a virtual outcrop model is just the reconstruction of the outcrop surface. But can also incorporate some kind of metadata, such as geological feature, surfacial properties, curvature, and whatever. Typically, virtual outcrop model, you know, almost all the people that working in virtual outcrop models know that there are essentially 2 kinds of representation for virtual outcrop models, point cloud and mesh. Well, point cloud is essentially an unstructured list of points with color attributes, while a mesh is a more complex object made of typically irregular triangles on which we used to drape some kind of images that we call textured mesh. Advantage and disadvantage of each kind of representation. On the left, we have a zoom of 16:4 of a point cloud. As you can see, at a certain point, the space between the points becomes empty. While using textured mesh, you still have the space that can be visualized, interrogated, clicked, and you can extract some kind of information. So generally, we love to work with textured mesh. The main disadvantage is that large textured mesh are quite computationally demanding, and you need to buy a high-level computer in order to work with this kind of model with a dedicated GPU. Traditionally, there are 2 kinds of technology that we use to build virtual outcrop model. The LiDAR and the so-called photogrammetry, which actually should be called structure from motion multi-view stereophotogrammetry, is a workflow made by at least 6 steps. Those 2 kinds of close range remote sensing technique has revolutionized, has implemented the use of virtual outcrop models in geology since at least 20 years. Well, the LiDAR, which means light detection and ranging, or also known as laser scanning, is just a rotating tool that measures the distance between the laser scanner and the object by measuring the return time of a laser beam. Pretty effective, a little bit less portable than the photogrammetry, widely used 20 until 10 years ago. Now the main tool, the main mode of scanning outcrop is represented by the so-called photogrammetry, which is structure from motion. Essentially, structure from motion works like the human vision system. We have different images of the same object taken from different viewpoints, And by connecting the same point seen in two overlapping photos, the photogrammetry software are able to reconstruct a 3D scene. Well, essentially, the photogrammetry is the science of making measurement by using photo. The down of photogrammetry is essentially the down of photographs. So this is the first no attempt of taking a photo, view from the grass in France. So about 2 centuries ago, it's the first photo. So the photogrammetry starts together with photo. However, the basic concept of photogrammetry are rooted in perspective and projective geometry that date back to the end of the Middle Age. Yet there are some attempts of projective perspective already in Roman times. Well, a little bit of math, but just to show you that there are some rules behind photogrammetry. Essentially, there are 2 rules behind the photogrammetry. The pinhole camera model, so the idea that we can connect a point seen in the space with a point seen in the photograph, and the rule is quite simple. It's just a linear relationship. There is some kind of distortion, and the overall package of rules that connect the point of interest through the point seen in the different images is called epipolar geometry. There is an epipolar plane, but it's quite, well, it's not that scary, okay? Just planar geometry. And the main disadvantage of structure from motion of photogrammetry with respect to LiDAR is that photogrammetry is not inherently metric. I mean, if you take a scan of a monument and of a model of that monument, you will produce the same object. So you need some kind of external control of some point in order to properly orient and scale the model. That was an issue about 10 years ago. Now, with the drop of the size and also of the cost of global navigation satellite system antennas that are already provided in typically in drone, but also there are some kind of very cheap and portable tools. We are able to produce high accuracy and high resolution virtual outcrop model and high precisely located virtual outcrop model with very portable tools, economic, and so this has allowed photogrammetry to overcome the laser scan at least since 10 years. Okay, so just to sum a little bit the story of close-range remote sensing in the last 50-20 years. The advent of LiDAR and structure from motion has essentially prompted the use of virtual outcrop modeling in geosciences since at least 20 years. The rise, particularly the rise of low-cost sensory platforms such as drones, smartphone, and reflex camera have further accelerated this kind of digital transition in geoscience, making virtual outcrop model essentially a standard in the study of geological outcrops. And at the beginning, I mean 20 years ago, 15 years ago, virtual outcrop models were just visualization tools, just a model that can be visualized and rotated. Now they have become a fully interrogable quantitative object from which we can extract a lot of geological information. So we typically extract bedding, fault, but also attributes such as the reflectancy and other kind of properties that allow to improve the interpretation of geological output. And indeed, in the last 10 years, the attention has shifted from the acquisition and building of virtual outcrop models, which is now a routine. It's just such as, it's like taking a measurement with a compass. We no longer investigate the model in which we build the model. We just investigate what we can do with that model, how we can extract geological information. So the next part, the next block of the presentation will deal with the extraction of geological surface from virtual outcrop model. Well, once you have your 3D model, you have to interpret this. The first step, sometimes is the only step that you achieve in 3D model interpretation, is collecting digitally the attitude of geological surface. That can be fault, fracture, or even just a bedding. Collecting the attitude of a digital 3D space is essentially finding a function or a set of functions that approximate the surface that we want to map. It's the so-called implicit modeling. The level of approximation is variable, depends on several issues, the purpose of the study, on the condition of the outcrop, and whatever. But essentially, it's reduced to the fit with just a planar function. So, in natural outcrop, and so also in digital outcrop, geological surfaces are generally exposed in two ways. There are the situation in which the outcrop map the geological surface. So the geological surface, a fracture or a bedding, is just the surface of the outcrop. That is something pretty interesting from the mathematical point of view, but is not that common. Much more common is the case in which the geological surface of interest intersect the surface of the outcrop. So the geological surface of interest is exposed just as a trace, a 3D trace. So those are the two end-member situations. Well, not two end-member, the two situations in which we can find the geological surface, and the two situations require different approach to extract the geological information. Well, there are various processes. So when we have the 3D surface that map the outcrop topography, it's quite intriguing from the mathematical point of view. And if you take the literature, there is a strong imbalance. Most, I would say almost all the totality of works dealing with automatic extraction of bedding and fracture from equal outcrop model are focused on this kind of situation. And there are algorithms that are automatic, semi-automatic, supervised, unsupervised. The real problem is that in those situations, using unsupervised or fully supervised approach, there is the high risk of mapping vegetation, slope, or whatever as a fracture, as a bedding, as a fault. So in the end, we spend much more time in cleaning our data set than in collecting data. By far, much more common is the situation in which the trace is exposed like this. Okay. In this case, the orientation data is obtained by analyzing the shape of the trace. And in particular, this is done essentially manually. We pick the point along the trace, and we derive the best fit plane that approximates this kind of polyline. There are essentially two types of approach to extract a plane from a set of points. The first is so-called best fitting plane with a remote RMS analysis, and then by far mostly used is the principal component analysis or tensorial analysis. Well, we skip this, the RMS. The principal component analysis measures the concentration of points along three orthogonal directions. And the direction of minimum concentration is the normal to the vector of the best fit plane. Essentially, I measure the minimum concentration, and the minimum concentration is the pole of the best fit plane. Why I'm insisting on this? Because in contrast with the RMS, the principal component analysis vectorial output includes quantities that are very, very useful to us in order to estimate the quality not only of the best fit, but also of the input data set. Because we want to skip the risk of taking for fracture or bedding something which is actually not exactly a bedding. Well, a little bit of math, that's the principal component analysis, which is rooted in this matrix, which is called covariance matrix. It's not that complex. we diagonalize this matrix to extract the eigenvector and eigenvalues, and essentially we use the eigenvalues to define the so-called coplanarity index and collinearity index. And what is actually, why are those two indexes so useful? Well, those are different shades of point cloud. This is a point cloud in which all the three eigenvalues are equal. When the three eigenvalues are equal, we have a spherical distribution, and the approximation of a spherical distribution by using a planar fit is just a nonsense. The same applies to this kind of distribution, a prolate ellipse, in which we have the maximum eigenvalues, which is just 3 or 4 times the intermediate eigenvalues. In this case, we have an oblate, and still the approximation of this kind of distribution with a planar fit is just a nonsense. It becomes more and more interesting when we have this kind of distribution. And those kind of distribution are characterized by a lambda 3, which is the minimum eigenvalues, which is tends to hundreds times less than the other two, which means that the distribution is essentially flat. And in this case, it is more than sensed to fit this kind of distribution with a planar surface. So, having this in mind, the desired characteristic of the trace that we want to map is that there is a high coplanarity. All the points must lie along a plane, and low collinearity. So we don't want the points to be aligned along a line, because there are an unfinished number of planes that pass across a line. So the question is, how much is ideal? Can we establish a benchmark, a values above or below which we have to discard the data? That's something we have done, but it's strongly dependent on the outcrop condition, on the exposure, on the kind of surface you want to map. It is a bedding, it's a bedding in a well-layered material, it's a bedding in a carbonate platform. So we have tried to incorporate different kind of exposition condition in order to develop some benchmark. And let me show you the problem. Okay, we start with a very, very basic scenario. Oops. Yeah. In this scenario, let's start with the first one. This is the topography of the outcrop, just a plane that intersect a perfectly planar bedding surface. The result is a line. Okay, in scenario 2, we have a rough surface that intersect a perfectly planar topography. In this case, we have a wavy curves. Then, a scenario which would be nice to have as a rough topography that intersect a perfectly planar geological surface. Then, by far the most common scenario, a rough and undulated topography that intersect a rough and undulated geological surface. Well, that's the starting framework. But then we have to enter in the digital world. The digital world is made by pixel. Okay, so if you zoom at a certain point, you reach this situation. And you have to consider the resolution of the mesh and some kind of tremor while picking. So if I start to pick this situation, because of pixeling, because of tremor, all my points will lie along the topography. So if I take this kind of distribution of points, they are highly collinear, which is bad, highly coplanary. There's a high coplanarity. But that's bad because the coplanarity is along the topography of the outcrop, not along the surface. The same occurs in this situation, even worse, because the geological surface is undulated. Well, the only situation which is quite good is this, in which my undulation are less important than the rugosity, than the wavy shape of the outcrop. Okay, that's the only situation in which I'm happy. Also, this is the situation in which I'm happy. So there is the key message is that there is an effect to the digitization of geological feature, which depend on the orientation of the outcrop. Let me explain you a little bit more in detail. That's a query. Okay. There are essentially three phases. Phase 1, phase 2, this is the pole, and phase 3, this, and this is the pole. And then the geological surface of interest in red, this one. Okay. What happened when I start to pick the geological? Okay, that's important. If I connect the pole, I have those kind of great circle. Okay, they are important. Let's store for a while here. Now I start to pick the trace of my geological surface here. What happened is that, of course, the pole is not here, but it's just lying here. Then I add another point, and still the best fit pole lie along this great circle. And again, and again, and again. Okay, I start to have a meaning best fit plane only when I start to pick this side of the wall, which is quite obvious. Okay, at that point I have a drop of the collinearity, and my best fit plane maps essentially is coinciding with the true orientation of the geological plane of interest. Okay, so when I have the drop in the collinearity, my data start to become well, meaningful. Okay, so detecting the role of the outcrop morphology on the best fit plane is quite straightforward if you are in a very simple situation like a quarry. What happened here? This is a rough surface. It's not a quarry. It's a natural outcrop with a wavy morphology. But how much is the effect of the outcrop surface on the digitization in this case? How can we derive a benchmark? So we have done this kind of experiment. We have used two approaches to digitize the trace of geological feature, namely the bedding, in two different ways. In a way, there was an expert user, me, basically, that using a visual aid was able to look at to preview the bedding, okay, the best fit plane. So I decided what is essentially mapping or not the bedding that was the bedding of interest. And the other opposite approach is just picking the trace without asking ourselves, is that correct or no? So we compared the statistical attributes of the two datasets in order to derive some kind of benchmark. Okay. Well, the first is the supervised at this preview, and the second was unsupervised without preview. Let me call expert and novice approach. This simulate the approach of an expert user. This simulate the approach of a master student that pick everything, okay, without asking if it is correct. So comparison of the result obtained from the two approaches allow us to set benchmark. We have done this in 8 kind of outcrop, different scale, different lithologies, and to differentiate a little bit the starting situation. And that's the result. Okay. In red, the pole by the expert user. In blue, the pole by the novice user. Let's focus on this. Okay. This density contour is just the contour of the triangle making the mesh of the outcrop. It's essentially the morphology of the outcrop. And if you remember the video, that's the grid pole connecting the morphology of the outcrop with the real bedding. As you can see, the novice is essentially digitizing the surface that are clustered along this grid circle. So, in order to do some quantification, we decided that this is the real bedding, and we computed for each datum the angular distance between the best fit plane and the real bedding. And that's part of the result. Just want to focus on two aspects. The angular divergence tells us how much the measure is bad. When we have an angular divergence of 40 degrees, means that the bedding is like this and mapped at something which is really, really at a high angle. So the worst results are here. Low number of nodes. Okay. And more important, the worst results are here. High collinearity. When I have high collinearity, the angular divergence increase. The coplanarity tends to have no effect on the angular divergence. Okay. So expert red, non-expert in gray, expert in red, non-expert in gray. And as you can see, when you are an expert, you already tend to discard the traits that have high collinearity. So now let's focus on just the non-expert user, and let's do some quantification. If we take this data set, okay, the collinearity index here and the angular divergence, you see that as the collinearity increase, the angular divergence, the error increase. So both the accuracy, I mean the average value and the standard deviation, both the accuracy and the precision is degraded as the collinearity increase. And last but not least, I take the two data set and I start to remove the worst datum. I mean, for each data set, I remove the data with a high collinearity. So by removing each datum, I essentially reduce the average collinearity, and reducing the collinearity reduce, of course, the angular divergence. That's also the maximum value of angular divergence. It means that here the average divergence is 3 degrees, but I have some outer layer of 15 degrees. And last but not least, this is the data number. The blue is the novice user. The gray is the novice user, but using only trace with a minimum number of nodes. I want to exclude the 3-point picking methods. Well, the result is that essentially, if we want to obtain some meaningful result, we have to discard all the traces with a collinearity above, let's say, 50, which means essentially more than 80% of the traces. That's an important message. Sorry. That's an important message. Also, in the data set built by using an expert and with the aid of a preview plane, I should discard more than 50% of the traces. That's something frequently overlooked. When you have a model, you cannot digitize everything. And typically, you have to digitize less than 20% of traces. Sometimes you have to deal only when the morphology is particularly flat. You can digitize less than 5% of what you see. Okay, so when you have a very nice 3D model, with high accuracy, high resolution, that model is good for visualization, but for data extraction is another story. And I'm time. Okay, that's the bed, that's the math. Now let's come to the nice story. All this stuff has very nice application and implementation in the geological mapping. I teach geological mapping. I like and I love the outcrop and field geology. And well, that's a very famous site of southern Italy, Grotta Romanelli. That's the entrance of a quarry. Grotta means a quarry. Cave, sorry. Cave Romanelli. That's the entrance of the cave. It's one of the first cave we discovery of Paleolithic in Italy. And you have vertical cliffs here. Okay, slippery surface here, vertical cliff. Safety issue here. So all the ingredients that make the remote sensing important. A little bit of information. It's located in the Adriatic coastline of southern Italy. It's one of the first cave with Paleolithic deposit, parietal arcs, stone tools. The cave opens in folded Cretaceous limestone and infilled with quaternary siltstone and sandstone and a roof collapse deposit, which is this one. Yet, it's incredible. There was no idea about the container. So all the infill is well known, well dated, but the age and of the container is not that known. The structural control on the speleogenetic process is not at all known. So we were asked to do a structural study of the container of Grotta Romanelli. Well, it's located in the Adriatic coastline, a little bit of geology, Oligocene formation, Oligocene calcarenite dipping toward the east, and in green Cretaceous limestone, essentially exposed here and here in the Romanelli Bay. Well, that's a geological map of the Romanelli Bay. That's an unconformity. We have two sets of faults striking like this and striking like this. And that's the outer limit of Grotta Romanelli. And there is an anticline in the Cretaceous limestone. It's really gentle and open. It's plunging toward the southeast. The flanks of Romanelli Bay are characterized by the Castro Formation, which is, well, a little bit unconformably on top of the Cretaceous limestone and is sealing this kind of normal fault. That's the entrance of the Grotta Romanelli. And the frontal view, very nice, with this open and gentle anticline, covered by quaternary breccia, and well, there are essentially two kinds of rocks that makes the Romanelli Bay. At the base, where this kind of lithified limestone is Cretaceous, well lithified, brittle, affected by faults, joints with a lot of flying disc and other strange animals. And on top, we have these very intriguing features. It's a kind of chalky limestone, you can scratch with a hand, and affected by deformation bands like this. And in microscope photographs, you can see that this is essentially a deformation band. This is a thin cataclastic layer. The material is porous, highly erodible, and affected by those kind of shear bands. Well, in this area, we have done our 3D survey by using a DJI Mini. So we took some hundreds of photographs of the bay. Then in the cave interior, we have used a reflex camera. And in some small passages, we have to use an iPhone with a LiDAR to bridge the outdoor and the indoor part of the model. We have used the classical photogrammetric pipeline with Metashape. And well, that's the result. Point cloud made by 750 million points. Typically, you have to clean a little bit the point cloud by removing low confidence value and vegetation. And after that, we have achieved a point cloud of 250 million points. We have used the 3D model for several purposes. Well, first of all, pretty important, you use that to do your own orthophoto in this kind of 2 centimeter pixel orthophoto, which has been used as a base map for field surveying. Then we have used the model in order to build an accurate stratigraphic section and accurately locate each sample. We have done Smith-Hammer, permeability, porosity measurement, so you can precisely locate your measurement in a stratigraphic section. But important for this talk, we have done other two things. First of all, we have mapped and we have extracted digitally the bedding and the fault orientation. And last but not least, we have used the 3D model to construct a set of slice of the Romanelli cave. Okay, let's start from the digital extraction of folds and bedding. That's the model. Well, on the right side, the stereograms with the poles of folds that have mapped digitally on the model. Okay, you have two clusters, this one and this one. On the left side, the folds collected in the field and the deformation bands collected in the field. And you do see that this is essentially this one is essentially this one. We lack this, but essentially because of a size problem. They are too small to be mapped in the 3D model. And last but not least, we have this set of deformation bands of shear band that is essentially parallel to this set. So the two data sets are somehow consistent, which is not new. Then, well, the bedding in the castle formation. Well, on the left side of the model, this is the bedding. And that green pole is this green pole. On the northern side of the Romanelli Bay, along this cliff, I have clinophone. So I have two modes, this mode, which is this, and this mode, which is this one. Then, next, the unconformity surface, which is slightly folded on the southern and northern limbs. So this one, which is this one, and this one, which is this one. And then last but not least, the bedding in the Cretaceous material, with the two maxima corresponding to the two limbs of the anticline, that again is placed here. So why I'm placing all this stuff here? Because as you can see, all the poles are clustered along a great circle, and I can take the pole of this great circle in analogy with the folding, with the study of folds. I treat this as a beta axis, and this becomes my viewpoint in order to view the 3D model in orthographic projection and have essentially an undistorted view of the geological structure. So that's the proper view direction, because I'm looking at the, well, in Italy we say traguardare, when looking in the proper direction with the advantage of having an orthographic view, so I don't have the perspective distortion. And once I have this, I can use this like a seismic section. And I can draw on that. And when you draw on that, you suddenly recognize that there is a prograding Oligocene material with clinoforms that is bypassing a fold, okay, in the Cretaceous limestone. And the Cretaceous limestone not only are folded, but it also show some kind of grow geometries. So this is telling us that the anticline is part of a Cretaceous tectonics. Now, zoom in the cave, in Grotta Romanelli. You will see the model rotating about a vertical axis. On top, that's the bedding measured in the field. That's the bedding on top, above the vault of the Grotta, above the roof of Grotta Romanelli. And here is the bedding at the base of the quarry. Okay, the bedding top. This one, this green, the bedding at the base, which is this one, okay, slightly oblique, and then I have a set of discontinuities within the cave that are clustered essentially in two big groups. One group is here is essentially halfway, in the midway, between the bedding at the base of the quarry, of the cave, and the bedding at the top of the cave. And then I have this second set. Okay. A view of Grotta Romanelli. That's the roof of Grotta Romanelli. This is the blue. This kind of fabric corresponds to the discontinuity that are halfway between the base and the roof of the cave. And in red, those kind of fabric which is oblique. Okay, close-up view. The blue and the red. But no apparent displacement, no one is cutting they are mutually intersecting. The problem is that the nature of this kind of discontinuity cannot be detected. You cannot take sample because there is a lot of the dirty material, and above all, there is this kind of parietal arc. So the discontinuities are essentially the base for parietal arc. So you are not allowed to take measurement. The same stuff outside the cave. This is the bedding measured above the roof, and this is the bedding measured below at the base of the roof. Okay, and that's the red fabric. So I've done the same operation, plot everything in asterograms, use the P-Greek plane and the bed axis as the Q direction, and that's the orthorectified model looking at an orthorectified view of the model, looking using this view direction. Of course, there is some breccia outside, but in the digital world, we are quite lucky. We can remove with no effort stuff. And that's an orthorectified panel removing the breccia at the entrance of the quarry, and that's the line drawing. So the bedding on top, the bedding at the base, and this, which is essentially this, is just the bedding. The red fabric, which is this, is essentially a fabric of soft sediment, early litification fault system. So we are essentially proposing that the cave is developed along an embryonic anticline, which is in the footwall of a low displacement sedimentary normal force. And that quite in agreement with the fact that we have deformation bands, so structure developed during the early stage of litification, that are parallel to this trend. And that's the geological cross-section. That material is a little bit lighter. Okay, that's the chalky high permeability material. That's the limit between the litified and the chalky material. And that's an embryonic normal force, which is characterized by discrete plane with no evidence of, no big evidence of shear. Well, having this framework in mind, we have done a set of slices of the quarry, okay, from the entrance till the end of the quarry. And as you can see, the morphology of the roof is essentially following the bedding and the falls, okay, like this and like this, like this and like this, which allow to tell us that the speleogenetic processes is going on by exfoliation of the roof. Okay, so essentially you have a slice made of bed, delimited by bedding and soft sediment faults that isolate those slices that are progressively exfoliated. And well, of course, we have done some kind of finite element modeling in order to assess the stability of the vault. Despite this red material, this red color here, the vault is quite stable. The basic problem is that this material is quite highly erodible, so the recommendation is to build an area here to prohibit working on this very thin bridge. And well, that's all. Just a kind of a few consideration. Well, the most important of all is this. That's something really important. Sometimes people that do field works are pretty skeptical with respect to virtual outcome model. On the other hand, people that deal with a virtual outcome model are not truly experienced in the field. But in my opinion, the potential of a virtual outcome model emerges only when the user is a field geologist, because it's a geologist that is used to look and recognize the stuff that you see in your 3D model. And well, that's all. 45 minutes. Perfect.
Thank you, Stefano. ¿Alguna pregunta?
Dime, si quiere en castellano, lo entiendo, lo hablo tal como el inglés, pero
Muchas gracias por la charla. ¿Cómo? Dos preguntas rápidas. ¿Cómo ¿Cómo hicisteis para localizar las fotos que hicisteis con la cámara fotográfica?
dentro de
Dentro de la cueva.
hicimos un único modelo. Entonces hay una grilla detrás de la grota y allí pusimos como 30 markers. Esto se ve de fuera con el modelo hecho con el dron y por dentro. Ok, entonces echamos los dos.
Y no hay problemas de escala.
No hay problema de escala, hay un poquito de problema de exposición, porque la cueva dentro está,
La luz.
no hay luz y además el tema es que hay mucha gente trabajando por allá, porque esta cueva se abre 10 días, una semana cada año y hay mucha gente trabajando, entonces no puede hacer lo que te da la gana, puede sacar foto allí en este momento. Y por esto el modelo dentro de la grota no es tan resoluto, como, tan bonito como es lo de fuera. Pero esto y utilizando el LiDAR del iPhone para hacer el bridge, al final no. Si lo comparas con el modelo hecho con el LiDAR de la misma cueva, hay un error que son 20-30 centímetros, que por este tipo de trabajo es nada.
Y otra pregunta un poco más esotérica, pero ¿podrías, tu opinión, cuánto tiempo habéis ahorrado utilizando modelos digitales? O sea, ¿cuánto tiempo os hubiera llevado a hacer este mismo trabajo, pero de manera artesanal? ¿Sí?
Allora, io credo che hemos ahorrado un tiempo infinito, porque esto no es que sería imposible, es un sitio bastante trabajado, hay mucha gente, esta cueva se conoce desde hace 100 años y es un sitio de interés. Nadie se había dado cuenta de varias cosas, porque el modelo 3D te permite de tener punto de view direction que en el mundo real no puedes tener, aunque no te ponga un jetpack, ¿no? Y cuando miras la misma cosa, de punto de vista distinto, es allí que te sale una idea. De nada.
Muchas gracias por la presentación. Aquí tenemos un equipo que estamos trabajando desde hace 6 meses en algo muy parecido. Nosotros también cogimos el enfoque de no trabajar con planos de fractura como otros softwares, por motivos, ¿no?, de que tienes muchísimo, si quieres identificarlos automáticamente, tienes muchos planos y además trace fractures, que planos tú puedas limitar. Nuestro objetivo también es sacar deep and deep direction, georreferenciado, pero aún no estamos aquí, estamos en la parte de automáticamente delimitar los trace fractures. ¿Habéis probado vosotros, en vez de hacerlo manual, de cogerlo automáticamente y ver cuál es la diferencia en los cabulsamientos de los seleccionados por un geólogo?
A ver, sí, sí, a ver, el resultado varía mucho y el problema es un problema, vamos a decir, filosófico. ¿Qué afloramiento usa por hacer la comparación? Porque el tema de desarrollar algoritmos y workflow por hacer automático, semi-automatic tracing, siempre hay una pequeña trampa que quien escribe los artículos no te dice, que este afloramiento ha sido elegido para desarrollar este workflow. A mí me interesa un afloramiento verdadero, porque cuando me voy al campo me sirve hacer una discrete fraction network por un tema de estabilidad de versante, ¿no? Por el tema del rockfall. A mí me sirve lo de allá, no me sirve uno que sea perfecto donde me salga la traza bonita. Entonces, cuando trabaja con afloramiento ideal, como podría ser de Zagros o de Pirineo, ¿no? Unos de Pirineo que son muy bonitos, que se ve el plano de fractura se ve bien. Esta es una cosa. Pero muchos de los algoritmos que se han desarrollado, cuando te vas al afloramiento, entre comillas, reales, fallan. ¿Por qué? Porque hay un patch y luego se interrumpe porque hay vegetación. La traza igual, ¿no? La traza, si hay una capa de calizas vacinal y margas y no está plegada, es muy sencilla. Pero si tienes una plataforma carbonatada, donde la capa está hecha por una superficie muy wavy y esta se interrumpe lateralmente, el geólogo, por suerte, el geólogo aún trabaja mejor que la inteligencia más o menos artificial, porque si tú te vas, por ejemplo, Network GT, ¿no? Que es el tool que tiene QGIS por hacer automatic tracing, te pasa más tiempo en limpiar la basura que en trazar tú mismo la fractura de mano. Esto es, de momento hemos llegado ahí. No sé con el tema de deep learning dónde llegaremos, pero la impresión que tengo es que cuando comparamos en afloramiento bonito, funciona la cosa. Cuando te pasas al afloramiento real, esto es bastante duro. Y es mejor trabajar manualmente. Te ahorra tiempo. O sea, parece imposible, pero te ahorra tiempo en trabajar manualmente.
Estoy completamente de la mayoría de trabajos son programamientos bíblicos. Y después hay algo que no he acabado de coger, que es lo de visualidad de planos de fotografía, como son minutos.
Vale, esto es. Mm, está. Ah, espera, Ok. Vale, en este software, ¿verdad? Este software, aquí puedes elegir dos opciones. Uno, voy haciendo el point picking y solo me sale la traza. Mientras que voy haciendo el point picking, me sale en semitransparencia el best fit plane. Así que yo puedo rotar el modelo y ver si este best fit plane es verdaderamente un best fit plane. Vale, esto es visualized.
Pero quiero ver si plane se saque de la media de los puntos.
El best fit plane es el best fit plane. Ya saco 4 puntos, me sale el best fit plane de estos 4 puntos. Añado un punto más, es otro best fit plane. Entonces yo cuando voy haciendo el picking, me doy cuenta si estoy haciendo un picking, por ejemplo, llego hasta aquí, ¿no? Y mi best fit plane es bastante bonito. Luego hay un pequeño folding, ¿no? No me doy cuenta porque el folding son de 4 o 5 grados. Allí veo que el best fit plane ya empieza a ser menos bueno, porque además tengo el control de visual, ¿no? Pero puedo mirar así y veo si este best fit plane efectivamente sigue la traza.
Ya confías un poco en la experiencia y olvidas de lo geólogo.
Esto sí, esto es coger la experiencia del geólogo y hacer de manera digital lo que hacemos en el campo. Te pone allá, mira un rato, es como coger una medida a 1 metro de distancia. Te pone la view direction perfecta y coge tu brújula y
Sí. ¿Y cuál es el software que utilizas para hacer
el software que lo he desarrollado yo se llama OpenPlot. Si quieres te lo enseño.
Sí. Vale. No.
Sí, gracias por la charla. Mi pregunta es sobre, has dicho que casi solo te quedan como válidos alrededor de un 20% de las medidas.
Si tienes suerte.
Si tienes suerte.
Claro, a veces cuando vas al campo y tomas medidas para validar los datos, hay cierta dispersión. ¿Esta dispersión natural, en qué porcentaje te puede afectar al final a la hora de validar tus resultados?
A ver, la dispersión natural es debida a varias cosas, ¿no? Muchas de estas cosas entra también en el tema digital, pero en el tema digital hay otro aspecto, que es esto. Tú puedes, porque tu manera de ver las cosas no es pixelated, ¿no? Si tú te acercas, ves. Si tú te alejas, ves con menos resolución. En el mundo digital, si tú te acercas, no hay un nivel de resolución que aumenta con tu acercarse. Entonces, este tema del efecto del afloramiento en el mundo real no existe. Es un problema que existe solo en el mundo digital. Es decir, la resolución la resolution y de la mesh. Y en relación al tamaño y la orientación del afloramiento es algo que afecta solo la medida digital. Luego, todo lo que afecta a la medida analógica también afecta a la medida digital. Hay un poquito de ruido, el hecho que las superficies no son exactamente planar, una pequeña falla o que te equivocas, has cogido algo que no es así. Lo único que no te equivocas es en leer la medida. De vez en cuando nos pasa que leemos la medida y reportamos en la libreta y la medida no está a 180 grados por la otra banda. Esto en el mundo digital no pasa. Digamos que todos los experimentos que hemos hecho de comparar datos medidos digitalmente y en el campo empalman bastante bien. Hay un tema de censoring, es decir, la cosa pequeña, tu modelo tiene una resolución, en base a esta resolución tú puedes medir datos en un range de dimensión, no puede ir demasiado abajo.
Vale, y bueno, y ya es una pregunta, entonces enseñan ejemplos de fracturas, estratificación, que son estructuras, pues, tirando a planares. ¿Habéis intentado aplicarlo a cuerpos un poco más heterogéneos, de forma, no sé, mineralizaciones más complejas o cuerpos ígneos, por ejemplo?
Allí entra en el tema de modelización no implícita, porque implícita quiere decir, tomo una superficie y le hago, de hecho, la tangente a la superficie. Y digo, esta tangente es representativa. Cuando hay cuerpos que son ondulados, allí entra en el tema de modelización explícita, y te sirve GoCAD, 3D Move, es otro, vamos a decir, es otro tema. Esto es coger medida de sitios en el cual tú no puedes llegar,
Vale,
a una escala en la cual tú no puedes llegar. Esto es.
una pregunta a mí.
Stefano, tú no estás trabajando de forma activa con nadie que está haciendo machine learning, ¿no?
Sí,
¿Sí?
sí. Y
Eso, sí, si estás trabajando de forma activa con alguien que está haciendo machine learning. Conozco algunos grupos de Italia y de América, pero no sabía cómo andabas tú con ese tema, porque, o sea, yo conocía bastante algoritmos, bueno, algoritmos, más bien training que han hecho en ámbito médico, y como siempre estaban siempre un poco en el futuro, pues le daban resultados bastante impresionantes, pero claro, no es una flor de piedras. No sé, igual.
a ver, hay varios campos del machine learning, del deep learning sobre esta cosa. Por una banda, hay el tema de modelización 3D, el hecho de los modelos virtuales. Allí hay toda un field de investigación que está a partir de una cosa que es espectacular, el intento de hacer modelos 3D a partir de una foto, una sola foto. Y el tema del mapeo, del tracing de las trazas, esto es un tema caliente, tal como, de hecho, siempre lo ha sido. En los últimos 20 años, los matemáticos han intentado. El tema es siempre lo mismo, es que actúan con afloramiento elegido para desarrollar esto. Y nosotros, cuando vamos a aplicar este tipo de algoritmo, el algoritmo falla. ¿Por qué? Porque aquí hay 4 fallas que te desplazan el afloramiento, te desplazan la capa, pero si no te das cuenta que son fallas, tú haces el bypass de la falla y la coge como un único. Entonces, seguimos siendo más inteligentes la inteligencia artificial, de momento, de momento. Muchos de nosotros, no todos. Ah.
Continuando un poco con la intervención que ha hecho Josep, nosotros sí hemos empezado hace 6-7 meses un proyecto que estábamos estudiando el open pit de una mina que hay en una faja pirítica, que son pizarras altamente texturizadas, y lo que estamos en el objetivo de ese proyecto es intentar caracterizar el sistema de fracturas lo mejor posible para luego ver, aplicar modelos de circulación de fluidos, porque justamente el problema que tienen es la penetración de agua de lluvia que les provoca deslizamientos porque hay sistemas de fracturas muy complejos. Y ahí sí estamos utilizando machine learning y que lo están llevando básicamente es, que he hecho la pregunta, Marco y también no sé si queréis en algún momento, pues podemos presentar el proyecto, habrá específico.
Me encantaría.
Porque sí que hemos empezado a trabajar en este sentido.
Yo también trabajo yo hice mi PhD sobre fracturas, entonces siempre es un tema que llevo, y esto lo aplicamos en tema de discrete fraction network. Hay varias cosas que hay que tener en cuenta. Esto no es la solución de todos los problemas. Tienen problemas de truncation, de censoring. Hay el tema que no todo lo que ve se puede medir. Hay varios tricks que se puede utilizar. Lo típico que se hace es utilizar estos modelos para ver en qué dirección hay que mirar la roja. Y luego, utilizando estos paneles autorrectificados, tomar medidas de length, de spacing, para popular los modelos de DFM, de hecho. Porque creo que lo que estáis haciendo es más o menos lo que se hace siempre. Se saca ley de scaling entre length y spacing del P21 y todos estos parámetros, pero cuando lo saca de un modelo virtual hay que tener en cuenta que hay un problema de multiscale, ¿no? Nosotros vemos una cosa en un range de dimensión. Hay que implementar también cosas a escala un poquito más pequeña y un poquito más grande para hacer un modelo de fracturación eso bien. Pero si quieres lo hablamos. Aquí estoy hasta viernes.
Si usted pasa que pero si están hasta el viernes, quizá podríamos buscar algún momento para explicarle un poco cómo estamos nosotros trabajando. Y por ejemplo, nosotros la experiencia que tenemos de modelos supervisados, incluso dando imágenes a geólogos expertos, hay un bias importante, porque en cuanto el modelo, o en cuanto digamos que el afloramiento real es complejo, la interpretación es distinta. O sea que ahí no es solo un problema de que, entre comillas, falle la metodología, sino que ya la propia interpretación, en fin, en geología tenemos muchos ejemplos que un mismo afloramiento uno lo interpreta de una forma y otro de otra. La verdad es que creo muchísimo y creo que el futuro de la geología está en apostar en desarrollar modelos de machine learning y learning para poder tener, digamos, estudios estadísticos importantes.
El problema de esto es el training. Yo he hablado un poquito con la gente que hace eso. El problema es el training, ¿no? Es que somos geólogos, como tú dices, ponemos 20 geólogos delante del mismo afloramiento, hay 19 opiniones. Entonces, ¿cómo lo hace el training? Que el training por machine learning
es modelos supervisados y modelos no supervisados. Es obviamente lo que tienes que intentar hacer. Nosotros, por ejemplo, lo que hacemos es no solo la interpretación, sino que luego lo mezclamos con datos de campo, mediciones de campo. Entonces, bueno, a partir de ahí se tiene que empezar en algún momento. Y yo estoy de acuerdo contigo que se está muy al inicio, pero se tiene que ir progresando pues, porque el futuro está aquí. No, no en mi opinión. Nada más, muchísimas gracias, perdón, porque
de nada.
antes no te he dicho, me ha parecido muy interesante el desafío. Discúlpame.
Yo un poco
A
los
nosotros,
datos, si los datos y el equipo que los trabaja, si los trabajamos es una persona, es muy importante.
¿Es una?
Es importante, pero también la aproximación. Si quieres trabajar con nubes de puntos, si trabajas con imagen y después con referencias, hay que ver, hay que comparar hay diferentes metodologías que se pueden explorar, ¿no? Y es un poco lo que estamos.
Sí, sí. Eso sí, la reproducibilidad de los resultados es un tema bastante central en todo esto,
Sí,
porque sigue siendo algo que si lo haces 20 veces y lo das a 20 personas distintas, ah, te salen cosas de vez en cuando dishomogéneas.
y tu trabajo de extraer planos de efecto es muy interesante, ¿no? Y resalta lo difícil que es. Solo que la interpretación varía un poco, ya cambia mucho.
Sí, sí.
Eso es lo que muy sorprendente.
Nada.
No creo que sea una cuestión no creo que sea una cuestión de elección de sistemas. O sea, al fin y al cabo, como decías tú, la cueva a mano, la que habéis analizado, así como en muchos casos, sin drones no lo hacías. Y así hay muchísimos casos de lo que ha pasado. No era tanto elegir, bueno, lo voy a hacer con brújula o lo voy a hacer con un virtual app. Llegó un punto en que ahí se había terminado poder ir con brújula y con virtual app te permite, dentro de lo que es un budget, dentro de lo que es la logística, hacer lo otro. A mí me parece un poco que con el machine learning va a pasar lo mismo. O sea, llega un punto en que no podrás elegir. O sea, si tú quieres analizar la cantidad de datos que pueden salir de la geofísica en ciertos tiempos, no sé, como en el proyecto que escribí ayer ahí en el Dolomite de Austria, llega un punto en que dices, bueno, o pones un ejército de geólogos, o pones un ejército de drones, o sea, de todas formas, esa cantidad de datos de forma sistemática no la vas a analizar. Está bien, pero o va a funcionar otro sistema, por eso me refiero un poco que en cierta escala todavía estamos en la transición, ¿no? Bien, fantástico, pero claro, en el momento que te llega una cantidad de datos excesiva, ya sabes cómo van las fracturas, o sea, te pegas un tiro, no puedes abarcarlo cuando las cosas se hacen de cierto tamaño, ¿no? Mi impresión es esta un poco, pero, o sea, que no va a haber opción B. Pero bueno. Eso le pasó al sistema médico, pasó lo mismo, o sea, las fracturas ya se han aplicado, o sea, ya los huesos rotos y bien salen mapeadas y están sacando los médicos porque no podían con los presupuestos de mirar radiografía por radiografía tranquilamente.
Sí,
Entiendo como médico.
está pasando lo mismo con la geología planetaria. Esto se hará de manera con la inteligencia artificial en geología planetaria. Esto no lo vamos a mapar nosotros.
No, claro.
Esto,
Bueno, digamos que estamos al principio y que obviamente es un camino muy difícil. Pero yo estoy de acuerdo contigo que cuantos más datos tengamos, más necesidad tendremos de tener.
es un camino difícil
capaces de-
y no solo es un camino difícil, es un camino que va a encontrar oposición. Porque el sentido común es que esto nos quitará trabajo.
Sí.
No, porque
Esto quitará trabajo a una cierta manera de hacer la geología. Pero esto puede ser, yo creo que esto puede ser el futuro de la geología. La geoscience, Big Data en geosciences es algo de importante, es el futuro. Ya hay unas cosas ya están hechas, hay varias cosas en geología que ya están hechas adelante. Movemos por delante. Pero hay un tema de oposición. O sea, esto fijáis que en la universidad en Barcelona es muy distinto. Vos tenéis la suerte que quien dio clase de field mapping utiliza tablet y esto. En el resto del mundo hay gente que delante de un tablet te dice que si no toma la medida con la brújula analógica, esta no es una medida. Esto existe y es la mayoría del mundo de la arqueología, también en el norte de Europa, y en Estados Unidos. Entonces, es un camino difícil y hay opositores.
Sí, bueno, yo para dejar el tema, un poco lo que dice la medicina al principio, pero oye, porque si conozco un poco este mundo, pues también hubo muchísimo rechazo. Y eso de que va a sustituir al geólogo, yo creo que no. Sinceramente, lo que dará, digamos, otro rol al geólogo.
Sí.
No será un trabajo tan de manual, artesanal, sino que...
Les asediaremos de geólogos que saben sumar y restar.
Eso
Esto es un problema.
¿Entiendes? Y no creo que, ¿verdad? Sinceramente no creo que vaya a sustituir al geólogo. Simplemente que se tendrá que definir un poco, como se ha hecho en medicina, el perfil del geólogo. Creo, ¿no? Pero en fin, es una pura especulación. Pues de verdad, muchísimas gracias.
No, a
Me
vosotros.
pareció muchísimo interesante y si queréis, pues podemos intentar buscar algún muerto y hablar.
Yo aquí estaré.
Ah, bueno.
No,
no.
tiene su contacto.
Sí, hemos metido algo.
El mundo es pequeño. Nos
Y
conocemos.
hasta el viernes.
Estaré hasta el viernes.
Bueno,
Muchísimas
Stefano,
gracias.
muchas gracias.
Vosotros.
Interesante.
Gracias.